Thank you, Phil, and thank you everyone for coming to my talk, Ensuring Data Integrity and Incident Response, Tools and Techniques for Forensically Sound Log Extraction. To go over a high-level agenda for today, I'm going to start by talking about why log quality matters during DFIR investigations, and dive into some of the limitations and potential issues that I've ran into when collecting logs directly from web applications. Then, when web-based exports fail, I'll teach you how to script out your own log collection tool that can circumvent some of those limitations that I mentioned before. During this section, we'll do a walkthrough of how to do this using a documented API, and I'll tell you about a time when I didn't have a documented API and I had to use some web app hacking techniques to extract the necessary logs. Finally, I'm going to talk about how important it is to verify that your log collection finished successfully and did not run into any errors. To assist in this process, I wrote a tool called the Log Anomaly and Validity Analyzer that I'm super excited to share with you guys today. Lava is basically a standalone executable that will parse your log collection, give you some statistics about the logs, and then alert on common errors within. So leaving this talk today, you will know how to write your own log collection tool using APIs, and you'll know how to use my tool to parse the output of your tool to make sure you didn't do anything wrong. Before I get into any content, let me introduce myself. My name is Colin Meek. I'm a consultant at Stroz Friedberg. Looks like I ran into a typo here. Sorry, folks. This is why you don't do live demos, am I right? So as I mentioned, I'm a consultant at Stroz Friedberg in our digital forensics and incident response practice. I'm based out of the Washington, D.C. office. A little bit about my background in cybersecurity. I was a computer science major in college, so I have a heavy software development background. My first job was as a penetration tester, and then from there I transitioned into DFIR. I use the skills that I learned in software development and penetration testing pretty much every week in my job in DFIR, and I think you'll see that in the presentation today. So getting right into things, why log quality matters during DFIR investigations. Reviewing logs is an essential part of any DFIR investigation. And you can look across the screens here today and just see some examples of log types that you might rely on in an investigation. Now, I might be crazy for saying this, but I think in order to perform analysis on these logs, you actually need to have the logs to do analysis on. This often means collecting the logs from wherever they live to your local system to perform further analysis. Now, this sounds really simple. However, during my career in DFIR, I ran into lots of issues that can impact the quality of the logs and therefore make or break the investigation. To show you some examples here, I'm going to start with the first limitation that I run into, limited native export capabilities from web apps. The example on the screen here is from a cloud platform event history interface, where you can look at the event history and download the logs. As you can see on the screen here, if you try to download too many logs, you get an error that says your download has reached the maximum event count. Lucky for us, on this interface, we can click Continue Remaining Download to continue the download. However, let's say that I have 300 times the maximum event count that I want to download. That would mean I would have to sit there, click that button, and wait 300 times. That's very manual, that's very tedious, and very error-prone. Another example here is in an EDR telemetry data lake, where I can submit a query for process creations. I get 54,000 matching events. I click download to CSV. It lets me do that perfectly fine. But when I look at the contents of my downloaded file, it actually only downloaded 10,000 events. This is a common issue when you run into web apps, and it's really just because this is a best practice when it comes to software development. You don't want to make it necessarily super easy to export large amounts of data from your environment. Another reason for this common issue is that a lot of these software applications just aren't designed for DFIR use cases in mind. A lot of times we've talked to vendors about this and we say, you know, we want to export more than 10,000 events. And they're like, why? Why do you want to download more than 10,000 events? That's just not what they're built for. The same way as, you know, operating systems are not built for DFIR in mind. We have to use the artifacts that are there and, you know, use them to our advantage. So when I run into these export limits, the first thing that I do, which I'm sure a lot of you would, is think, how can I filter down my query to make it so that I you know, get an event count that's under that limit? As you can see back in the cloud platform event history, I can filter on things like event name, event source. One thing that you can't filter on here that I think would be useful is IP address. So in order to perform IP-based analysis, I would need to download a larger data set and perform IP-based analysis locally. So what next? I run into these issues a lot, and as a result, I've often written my own custom scripts to get around these limitations and pull the full log set. After you finish your collection, it's very important to verify that you have what you expect. Now, to show you what I mean when I say have what you expect, I want to tell you about a ransomware case that I worked on recently. As in most ransomwares, a common objective is to determine how much data was exfiltrated from the environment. And as many of you probably know, a common evidence source for that is the traffic logs from the firewall device. So this client did not have a strong internal security team or a SIM. So we had to go to the web application of the firewall device and download the week's worth of logs during the malicious activity. So we did this. It resulted in one large log file with, and we took a quick peek at it with PowerShell, and we see that there was, the top time was almost the 11th, the end of our malicious time frame, and the bottom of the file was the 4th. So we figured we got everything we want, and we started to perform analysis. During this analysis, we weren't seeing a lot of the common things that we would expect when data is exfiltrated from the environment. We weren't seeing large transfers of data to weird IP addresses in a short time frame, nothing like that. And when we started to graph out these events a little more, we saw this pattern emerge that you can see on the screen, where there was events on Sunday and Monday, nothing from Tuesday to Thursday, and then events back on Friday and Saturday. Now, can you imagine if I told the client, yep, there is definitely no data exfiltration in your environment, you are all good. And then, down the road, I get called to the stand and opposing counsel pulls this graph up and says, really? You claim there was no data exfiltration when you clearly had this large gap in visibility? That would not be good. So moral of the story here is it's important to be aware of your gaps in visibility so that you can complement them with other data sources. So to go over the potential issues that we've seen so far, oftentimes I run into export limits, issues filtering the data before I can export, and gaps in logging. All right, so getting into the fun part of this talk. Let's do this together. We are going to build a log collection tool using a documented API so we can circumvent some of these limitations. For this example today, I'm going to be using an EDR data lake API. And just to make it simple and straightforward, our objective is going to be to download all process creations from June 1st to June 15th. I'm going to write this tool in Python, or I wrote this tool in Python today. I'm not going to actually show you a lot of the code, but these are some of the variables that I would hard code in my tool. If you were to make it a better, more versatile tool, you might make these command line arguments so that you could pass in any query and any from date and to date. So roadmap for today, we are going to first set up our authentication, which with most websites, it's just browsing to the website, downloading an API key, and putting it in your code. Then we are going to create a query at our first endpoint, API endpoint. We're going to go to our second API endpoint to check the status of that query and see if it's finished. Once it's finished, we're going to go to the third API endpoint to collect our sorted events from the finished query. I'll touch on this a little bit after the last step here, but the sorting is really important because when we sort our events, we have a deterministic way to know that we got everything from our minimum date to the maximum date that was actually collected. After we do this step of paginating and getting our data, we're going to verify that our expected logs were collected. And if they weren't all collected, we are going to perform sequential queries to get the rest of the data. The reason this performing sequential queries works in a forensically sound manner is because we sort, mostly I just do it on time. You sort on time, and you know that you got that chunk of time, and you can requery for the remaining chunk of time that you need to collect. So those are the steps we're going to go over today. I'm going to take a step back and, because all APIs are built differently, go over just some of the common considerations in general that I think about when using a documented API. The first thing that I talked about earlier is there built-in querying and filtering? If you can limit down the number of events before you collect, that'll make it faster and just easier. You can always go back and collect more events later. Does the event collection API endpoint support pagination? What I mean by this is breaking up a larger set of data into more digestible chunks and collecting them once at a time. Are events queried and returned from one API endpoint or multiple? What I mean by this is some more basic APIs have one API endpoint where you submit a query and you get the results back from that same endpoint. Other more advanced APIs, like we're seeing today, have one API endpoint where you submit the query and a different one that you collect them from. The last two here go into what I mentioned before on if there's a limitation on the total number of events returned, does it support sorting so that we can deterministically know what we collected and perform sequential queries? Okay, finally into the actual steps. Step one, we're going to set up our authentication. To do this, I just went to the website and see how their authentication works. I get an API token value, and it tells me to use the token in the request header like you see on the screen. This is pretty much the only code you're going to see here today, but the reason I think it's important is that the whole goal of this today is to take what you read in the documentation and implement it in your code so you can use it in a programmatic fashion. One other thing I want to touch on here is that you notice that I don't actually put my API token in my code. It's always best practice to keep that critical authentication in something like an environment variable and retrieve it within your code like you see on the screen. Once we set up our authentication, we can use that to go to our first API endpoint called init query, where we can send a post request with the from date, the to date, and the query, which we defined earlier is going to be process creations from the 1st to the 15th of June. And this endpoint will return to us a query ID that we will use later on. Something else I want to touch on this slide is that you can see there is a limit. On the screen here, it says it's 1 million. In my case, it was actually only 200,000. But for now, we're just going to glaze over that, pump it up to the maximum, and we'll talk about it later. So this is a basic representation of what your request and response would look like. You would implement this in your Python code or your preferred scripting language for the query, from date, to date, and the limit. And in response, we get our query ID. Once we have this query ID, we can go to our second API endpoint, query status, which is a pretty basic endpoint where we send the query ID, and it will tell us the progress status, which is a percentage of how much the query is finished, and the state, which is an enum of is it running, is it finished, is it timed out. So I'm going to make a function that gets this result and intermittently check in a while loop until the query is finished. You can see on the screen here that it's just printing out once a second. Progress status is 0, 11%, 29%. Finally, it's finished. Once the query is finished, we can go to our third API endpoint, this get events, where we'll submit some extra stuff in the request, which I'll show you on the next slide. But what it will return to us is the data, which is important. You can write that to a file, append it to a list, whatever you want to do. And we might also get back a next cursor value. This is what I mentioned before in pagination, is what we'll use to get the next chunk of data. This is a high-level graph of the process that I would perform here, where I submit the query ID, telling it to sort on time, because remember, that's very important to make it a deterministic chunk. And it'll respond with our most recent event data and a next cursor value. This next cursor value we can then use in our next request, and it will return to us the next chunk of older data. So if you weren't familiar before, this is what pagination is. We're paginating until we get a response with no next cursor value. That means that we have retrieved everything from the query. So this is the output from my code. You can see the red block is some stats from the first response, has the most recent chunk of data, and you can see it just goes back in time, back in time. All right, so we did that, we paginated, we checked until it was done, we're finished, right? We have everything that we need. Wrong. Remember, I told you earlier there was a limit of 20,000. And if we look just with PowerShell at our output, we see that the most recent event is almost the 15th, like we expect. But that bottom event in our file is only the 10th. And we really wanted to collect all the way back to the first. Let's take a step back here and abstract everything that we've done so far today into a function called perform query. This function, we will submit a query, a from date, and a to date. It will do everything that we talked about previously, where it'll start the query, check until it's finished, paginate, collect all those events, write them to disk, and it's going to return to us the number of results that it collected and the earliest date that it collected. Because remember, it's collecting in descending order. With a function like this, we can perform the following process, where we submit our first query with the actual time frame that we want to collect from. And if we get a number of results that is exactly 20,000, we know that we hit that maximum export limit. What we can do now is, because we sorted, we can take that earliest date that we know we collected everything back to and use it to update the to date and perform another query. So as you can see, we update the to date, perform another query. If we get 20,000 events again, we know we hit that limit. I think you can see the process here, where you do this until the number of results is something that's less than 20,000. So now you can see that same stats is that my count is something that's a lot more random and kind of expected in an event count. And the top timestamp and the bottom timestamp are what we wanted from the 1st to the 15th. So just to go over the steps of what we did today, we set up our authentication, we created the query, checked until the query was done, paginated to collect those events, checked to see if that actually had everything we wanted, and if it didn't, we performed sequential queries. Let me take a drink of some water here. All right, so that was really nice. We were able to read this documentation and build our tool around it. But I want to tell you about a time when I didn't have any of that documentation, and I had to figure out what to do. To go over this, I'm going to go over an anonymized case study of an APT case where we're going to call the company Nimbus Core Technologies that had a tool Lightning Log Store. Some background of this case, Nimbus was the victim of an APT breach, and they had an internal tool called Lightning Log Store, which was a web application that had a data lake of internal process data. You can see what it had on the screen is what was in the web app. It had information like the PID, the parent PID, the name, the command line, and so on. We found some custom malware in the environment that we wanted to see what commands were ran through that malware. Lightning Log Store did have basic querying capabilities where you could query on the PID or the name and so forth. However, there was no built-in functionality to create process trees on the right here, because that's what we wanted. So what's a way that we can script out a solution to get this if we know that we can query and get results? The way that we can do this, it's pretty straightforward. We query to find the malware. We get its PID. We query for any other processes that have a PPID of that malware's PID. And then we just recursively perform this hunt until we have all of the bad stuff. We just learned how to use APIs. This seems pretty easy, right? We can just use an API and script this out and collect these logs, no problem in our code. Wrong. Unfortunately, Nimbus Core Technologies was not aware of any API interfaces in their application. Since we had read access to the environment, they told us that we could do whatever we needed to extract this vital information. Now, I want to emphasize the importance of permission there, because what I'm about to walk through is web app hacking techniques. So it's really important to get permission from the owners of the data and make sure they know that you're doing this. So the script out a solution, the entire solution is very similar to the previous example with the documented API. However, there's just some steps that we need to do before. These steps, we're going to start by setting up a web proxy tool. I use Burp Suite. However, you could use any proxy you like, or even the built-in network tools in a browser. Then we're going to perform the action we want to automate, which in this case, we want to automate performing a query and retrieving the events from that query. Then we're going to look in our proxy and find the backend request that was actually responsible for performing that desired action. We're going to replicate that request, and we are going to try to narrow down what parts of that request are actually necessary to retrieve the results that we want, that process information. So first couple steps are pretty basic. I combine them here. We set up Burp and perform the action we want to automate. I obviously don't have access to the Lightning Log Store application. So for today's purposes, I'm using OWASP Juice Shop, which is a known vulnerable web server. The reason I use this is because it's open source and it serves all the purposes. The action that we want to automate today is going to be just getting the profile page of the website. However, again, in our real case, it was performing that query. Once we perform that action, which was getting the profile page, we're going to go to our HTTP history and try to find the request that actually got that HTML for the page. One straightforward way to do this is just scroll through the request and look at that URL and see if it's something that matches the name. Like in this example, it's get profile, pretty straightforward. But what you also want to do is once you find something that you think might be the request you want to replicate, you really want to make sure that that response contains the data you need. So if this were the example of the Lightning Log Store, I would want to make sure that this request actually returned JSON or however formatted data that I could use in my tool. Once we find this request, we're going to replicate it, which in Burp is very simple. You can send it to their tool called the repeater, where you can edit the request and send it and try different things. Once we have this, our goal is to identify which of these headers are really needed. The reason I do this is because, remember, the goal of this is to replicate this request in our code. And I don't want to have to hard code all of those headers in my code. I just don't want to do that. I want to figure out what's actually needed to authenticate and get the response that I want. So let's just take out all of those headers and see what happens. I send the request, and I still get a 200, OK, great. I don't need to hard code all of those headers in my code. Next, I see there's still like 4 cookies here where I don't think I need all of them. So let's take out the token value. And I get a blocked illegal activity. Looks like we do actually need that token value. But these other things, continue code, language, I don't think we need that. So I'm going to take those out, put back in the token value, and you can see we get a 200 OK. What we learned here is that now we have this very small request, and we realize all we need is this cookie value and the token, and we can get the response that we need. So what's the point of that? Well, the point is that now we have a programmatic authentication mechanism that we can put in our source code, just like we did before, and use it to programmatically use this endpoint like an API. So just to go back to the previous roadmap of the documented API, we're basically right back up at we're finished with the first step. We set up our authentication. You could now go through and do all of the same process that we did before and script out a tool. I'm not going to go over that today because we already did it, and I think you get the point. All right. So what I know you've all been waiting for this whole talk, you haven't cared about anything else before, the log, anomaly, and validity analyzer. This is a tool I wrote that will, as I mentioned, parse a given log set, generate statistics about the logs, and then alert on common issues within the logs. It currently supports CSV files, JSON-L files, and any unstructured plain text log file. It's written in Rust too, so it's a lightweight executable. You can just download from the GitHub and run it without having to install poetry or anything like that. To show you how useful this tool is, I want to take you back to some examples that we talked about earlier in the talk. You remember this case study with the ransomware where there was one big log file, and we realized after a while that there was this time gap in the middle. That was a pain to parse and to realize that fact. Would have been really nice if there was a tool that I could just run and snap, it would tell me, boom, lava. We run lava on that output, and we see a high alert that one file has a largest time gap greater than 30 standard deviations above the average time gap. That's kind of a mouthful of words there, but the reason I created this alert to be custom to the specific target log file. If I were to hard code these alerts to be, alert on any largest time gap that's larger than 10 minutes, 20 minutes, whatever, that would be different based on different log files. Some log files, like process events, are going to be, at least one every second. Other things like authentication logs or badge logs are going to be much less frequent. So this alert will look at, in the context of the specific log, how out of the ordinary is that largest time gap. This is a small log file, but you can see finished in 0.00 minutes. Wow, pretty fast. But this is just the command line, and it also generates a output file with more in-depth statistics. As you can see, at the bottom is from the statistics file, where you can actually look at what is that largest time gap in your logs. Another example, if you remember in our step 5 of the documented API, we realized after we finished that we had hit that event export limit. Boom, lava. We run lava on it, and it says, high alert, one file has an event count divisible by 10,000. The reason I alert on that is it's pretty unlikely to have exactly 10,000 or 20,000, however many events. I guess 1 in 10,000 to have it be rounded by 10,000. So that's something that's a pretty strong indicator that you ran into an export limit. So I gave you examples of the unexpected time gap alert and the unexpected event count alert. Those were both highs, but it also has medium and low alerts based on how unordinary it is. Some other alerts that I'm not going to actually show you, but I want to highlight are it will search for redacted fields. So if you think you have all of your logs, but some fields are actually redacted that you might actually need, it'll look for common strings that indicate redactions. when you're creating log collection tools, it's very common to have duplicate events if if the time frames are inclusive. If you're collecting from this time to this time and then that time to another, you might have duplicate events. It will alert on that. It will also alert on JSON formatting errors, that can be a problem when you're trying to ingest your logs into another tool like Kibana or Splunk. This is another screenshot of the terminal output. I didn't go over it. In the previous examples, I was parsing one log file. However, you can parse as many as you want. It's a threaded executable, so it'll parse each file concurrently. One other really cool feature that I like, it's straightforward but actually really useful, is that it'll tell you the total number of records that it processed. This is really useful because I don't know if anyone else has ran into instances where you ingest 20 log files into Splunk, and because of the checksum or the CRC checks of the beginning of the file, it thinks that two files are identical and only ingest one. That's also something that's really important to know. So I'd highly recommend running Lava after you ingest into Splunk and just compare that total number of records that Lava saw versus the total number of records that actually got ingested into Splunk. To go a little bit into the workings of how Lava works, for its timestamp analysis, it needs two things. It needs a regex to capture that timestamp and a Rust, what's called stirf time format, to parse the timestamp into a real-time object. I compiled the tool with lots of these timestamp formats built in, so hopefully you can just run the tool out of the box. However, I'm sure that I missed some, so I also made it so that you can pass a file like you see on the screen at runtime, and it will use that timestamp format in its parsing. Another thing to note, this tool is open source, and I made it pretty much identical to this to build these timestamp formats into the tool and compile them in. So if you're using the tool and you come up with a cool custom timestamp format that's not already supported, contribute. Build it into the tool, and build it into the tool. It's very similar to like what you see on the screen, and you can help people in the future. Some other useful features that I want to go over. I mentioned duplicate and redaction alerts. It will also actually extract those lines to a separate CSV file, so you can quickly just take a look and see, what redaction rule did it hit on and where. It will also hash files for evidence purposes. If you don't care about file hashing and duplicates and redactions, I implemented a quick mode, which will skip those and just do the timestamp analysis, which, in my opinion, is the most useful part about this tool. Event counting, we already really talked about. So the last feature I'll mention is time field specification. As many of you know, lots of logs will have multiple timestamp fields. So by default, Lava will just use the first one that it finds. However, you can pass a command line argument and tell it to use one of the different columns or JSON keys for its timestamp parsing. All right, that's all I have for today. Check out the Lava GitHub, scan the QR code, and thank you for listening.